Markov chain. This was a numerical example. So we got two states, 0 and 1. We have these transition probabilities, which are pictured as arrows, which are going from one state to the next. We have a bunch of random variables that tell you where you are at points in time. So this was x0, x1, xn tells you where you are at time n or day n. We defined an initial distribution or initial probability. In this case, it was 20%, 80%. And in this case, the transition probabilities, which really mean if you know where you are one day, what's the chance of being somewhere else the next day? They were defined to be these. These correspond to the arrows. I think our next page. Next page, we did some calculations on how to find the distribution at day 1 and how to find the distribution at day 2. And the main tool was the probability tree, which means the main rules that we used were to use the multiplication rule and the sum rule. We've talked about some of those rules already. I guess I gave you homework to find pi 3 and pi 4. How did that go? Maybe I did pi 3 in the office hour, I'm not sure. You're very quiet, so let me ask you again. Did it go okay?
I didn't think it was that hard.
I think it was fine.
Yeah, it should be similar to these two calculations, right? Basically. Great. Then we generalized the whole scheme. And we took away the numbers and put in P's and Q's to represent the transition probabilities. And I guess here was the second homework problem, is to find the distribution of x2, where you are at day 2. And it looks like, I think this is what we thought the answer was. Let me scroll down a little further. So this is just a recap of what we did the other day. And we figured out these formulas. So we did symbolically what we'd already done numerically. We figured out two formulas. We figured out pi 1, that was sort of done first. That's up here. So pi 1 of 0 turned out to be this, and we just figured it out the same way. We just multiplied, well, up here, pi 0, 0 times this, and pi 0, 1 times q. And the calculation is here. And that's how we found pi 1 at 0. And then you could do pi 1 at 1 in two different ways. You could do the same calculation where you end up at 1. But I think all I did is say that pi 1, 1 would have to be the complement of this. So I just subtracted this from 1 and got a formula. And then we did it a second time. Usually, again, it was really the same ideas that we had done with numbers, but now where we're using P's and Q's. P's and Q's, and we were using pi 0 and pi 1, pi 0, 0 and pi 0, 1 instead. And so we came up with this answer. So these are the two formulas we had. And this one's boxed. This is just pi. So pi 2 was the distribution or the table at day 2. And it's asking what's the probability at day 2 you were at 0. And the probability of being at 0 on day 2 turned out to be this expression, which really just depends on the P's and Q's, which are the transition probabilities, and the initial distribution. I think I've got my distraction right on time here. Friday afternoons or mornings, I guess. I'm maybe battling a lawnmower. So if you have trouble hearing me, let me know. I'll turn up my volume. My window's closed, but the lawnmower is close. Okay.
We can't hear it. It sounds fine right now.
Okay, good. Well, I'm confident you will because I see the person approaching, but he's moving pretty quickly, so he'll come by my window, and I think he'll leave it pretty soon. Okay, so where was I? So we actually went through the calculation. We boxed this formula. We did that's the chance of being at state 0 on day 1. And then the chance or probability of being at 0 on day 2 turned out to be this formula. And in general, the book then says that the probability of being at 0 on day n turns out to be this. So, and I'm not sure if I said anything more on that. Let me see what I did on the next page, if anything. I may have run out of time with that. Yeah, this was the following class. So that was it. So let me pick it up from this point here. So this is a pretty impressive formula. It's telling us at any time n, any day n, what's the chance of being at state 0? And remember, go back to the picture here. If we got it somewhere, there it is at the top. From one day to the next, we could be flitting back between 0 and 1 with these probabilities here. So I think I said last time you can prove this. I may have said this. You can prove it with induction, and that I don't think I'm going to do it. But I thought twice about it, and I thought, well, if it's not too bad, maybe I should prove it. So I did write up a few notes on that, and I think I'll go through it. Because it's not the most intuitive formula in the world, but it is based upon what we've done before. So I hope you're all okay with this formula, and it's actually this idea and this formula. So let me see if I can. Should I press my luck and try to get it on this page? Why not? Let's see if it works. All right, so let me get to my notes. Okay, so this is the claim. We want to see that this holds for not just n equal 1 or 2, which are the two cases we have. We want to see that it holds in general. And what I'm going to do is essentially a proof by induction. I'm going to show that if this is true for n, then it's also true for n plus 1. And a proof by induction, you start off by showing that it's true when n is 1, and we've done that. You may have to think about it, why this is a special case of this. But if you just said n equal to 1 in here, this becomes just one term in the sum. And you have 1 minus p minus q times pi 0, 0, which I think is the same as this, yes. And the one term here, the first term would be 1 minus p minus q to the 0, which would be 1. 1 times q is q. So this formula agrees with pi 1. So let's assume now that it's true for n and try to see that it's true for n plus 1. So that's the idea of an induction proof. So let's assume the box formula. This box formula holds for n. And let's check. That it still holds. For n plus 1. Okay. So we get to assume this. And here's, it's basically the same picture we've been using. So assume here we got this tree again. And suppose this is really not the full tree, it's the last part of the tree. So here is where you're at day, this is where you're at day n. And over here would be where you're at day n plus 1. So at day n, you're either broken or you're working. At day n plus 1, you're either broken or you're working as well. And oh no, let's see if we can cover this. So you see, try again. All right, I recovered it, but that doesn't bode well for this. Let me make sure you can see it all. Okay, so I assume you can see it. Let me see
Yep.
if be a little more careful with this tablet, see if I can avoid. So what I was saying is at day n, you're either broken or you're working. And the same is true for day n plus 1. Oh, I give up. I should just go to the different screen. So sorry. Let me just try it again. All right, so it doesn't like. I pushed my luck and it told me not to do it. By the way, I'm not doing anything, but it's very sensitive. So let me see if I can get this again. There it is. Okay. Okay, so remember this formula. I'm going to transfer it as soon as I can to the next page. So let's go to the next page because this isn't getting it done. Let's put some lines on this page if I can. Okay, so it's letting me do that. Okay, so the one that I get to assume is this one. P at time n equaling 0, the probability that at time n you're broken is 1 minus p minus q to the n. times the probability that initially you're broken, plus the probability, or Q, times the sum that goes from j equals 0 to n minus 1 of 1 minus p minus q, all of that to the j power. So this is what I'm assuming. And we're trying to, we're assuming it's true for n, we're trying to get the same result for n plus 1. And the idea was to draw that picture. This is where you are at day n. And this is where you are at day n plus 1. And so the probability of being here at day n is this. So the probability of being at this point is exactly what we have. The chance that time n you're there. And over here, you're either broken or working. So the chance of being broken at time n and then being broken at time n plus 1, well, that would mean that you stay there. So remember how the transition diagram looks. The transition diagram looks like this. This is P, this is Q. This is 1 minus Q, and this is 1 minus P. So the chance that you're still broken here is the chance of looping, which is 1 minus P. And I can label this as P, but I don't need that. What I need is this one. The chance that you're here is the probability that at time n you're at 1. And then the chance of being broken on the next day would be going from 1 to 0, which is what, Q? So what I need to do is figure out the probability of ending up being broken at day n plus 1. Okay, and that's assuming I know the probability that I'm broken at day n or that I'm working at day n. So what I'm suggesting from this little tree is the probability at day n plus 1 that we're actually broken would be the probability that at day n you were broken. And you're still broken the next day. So you multiply the probabilities together. So this would be 1 minus P plus the probability that at time n you're actually working times the probability that you broke in the time from day n to n plus 1. So the tree is how we figured out pi 1 and pi 2 to begin with. And we're using the tree again in general now, assuming that one step back is where we are at day n, and the next step forward is where we are at day n plus 1. Okay, so doing the induction really comes down to what? Following. So this calculation, let's just do it again. It's the chance that you were broken at day n, but that's all of this stuff. I'm not excited about writing that, but I don't know a way around it. So it's 1 minus P minus Q to the n. P at time 0, you're broken, plus Q times the summation from j equal 0 to n minus 1 of this stuff, 1 minus p minus q to the j. So it's all of that times 1 minus p. Plus what is pi n1? Well, pi n1 is nothing more than pi n1 is really just the complement of the other one, pi n0. So how do you do the complement? You do 1 minus this. Because these two probabilities add up to 1. You're either broken on day 1 or you're not. So it's the chance that you're not broken, which is the complement of being broken, times q. Okay. And, well, I sort of have a mismatch here. I've substituted in what this thing was in here, but I didn't substitute that same nasty expression in here. So let me write it one more time, hopefully. All of this stuff is 1 minus p minus q. And probability that x naught 0 is 0 plus q times the sum. And inside the sum is 1 minus p minus q to the j power. All of that gets multiplied by the 1 minus p. Now we can get to this thing. This would be 1 minus the same expression here. Let me see. Oh, I see what I did before. I did it more cleverly. Okay. Let me back off a little bit. This is working, but I think I can do it in a shorter way. Write these expressions many times. So all I really did before substituting in what the expression is, just simplify it from here. So this one would be the probability that the time n you're broken times 1 minus p plus the probability of time n you're working. Well, that's this 1 minus p n times q. Okay, and so what's easier to do here is just multiply everything out and regroup. So this times this is the probability that a time n you're broken. And minus p times that. So I just multiply through by these. And then this, q, distribute that, you'll just get a q. And distribute this product, you'll get a minus, I'll put it down here, q times the probability that at day n, you're broken. So I'm just multiplying, distributing the Q. And if you do that, well, what do we know this all is? Well, this is all still this, right? This is still the probability that at time n plus 1 you're 0. So that's still, you can put that over here. This equals this. Okay. But in the meantime, I've lost something here. What did I lose? Probability that at time n is 0. Minus the probability that time n was 0 times p, right? Yes. Okay, so what is all of this now? You can just group this term with this one, They all have the same factor, p sub n equals 0. So write that as probability that at time n is 0. Factor that out. Well, what will remain? What would remain is this 1 minus p minus q. And then the only thing else that's left here is plus q. Okay, so that's easier to do than writing in this nasty expression all the time. And we have it all now in terms of what you were at day n, the probability at day n you were at 0. Okay, so hopefully I didn't lose you in that transaction. Is that clear, I hope? Okay, so at this point, put in what this is. Now, but that's equal to this stuff. So now I need to write it that way. So this is going to be, by the induction step, essentially, 1 minus p minus q to the nth power times the probability that at day 0 you're at 0 plus q times this summation j equals 0, then minus 1 of 1 minus p minus q to the jth power. So that's what that is. That all gets multiplied by the 1 minus p minus q plus q. So again, remember, we're assuming this. We're assuming that Pn at 0 is equal to this stuff. And so all I did at this point is put that in for Pn at 0. That's what it equals. And so now we have an expression for where we are at day n plus 1. So at day n plus 1, the chance that we're at 0 then is equal to all of this. Now, what comes quickly is you can just distribute this product through the sum. And if you do that, you'll get 1 minus p minus q. And now it becomes to the n plus 1. Because this base is the same as this, times the chance that at day 0 you're 0. Plus q. And you can product this sum by bringing it through the summation sign. And if you do that, you'll get j equals 0 to n minus 1. And in the summation, you get 1 minus p minus q. And you just add the exponents, you make it j plus 1, and then there's plus q. Okay, so it's pretty much algebra at this point. The only probability was involved was the tree, figuring out that we had to go down the top road or this middle path. And those are the two ways we could be broken on day n plus 1. Okay, now to get this to look like what we want, well, what do we want? I didn't show what we wanted, but it's this where you replace n by n plus 1. But this already has an n plus 1 there. So this term is in fine shape. The one that we have to massage a little bit to put it into the form we want is this one. So let me do that. So this is now equal to 1 minus p minus q to the n plus 1 times the probability at time 0 being broken. And what we're going to do with this, in order to get it to look like what we want, we're going to lower the index on the inside by 1 and offset that by increasing the index in the sum by 1. So if you lower the index by 1 on the inside and increase it by 1 on the outside, you've essentially not changed it at all. Now, you may have to think about that a little bit, but that's true. So if I make the index inside here 1 less than it is, then it would become j. And if I make the index on the inside to be 1 more than it was, then I'd be going from 1 to n. And I'm suggesting that if you do that, you still have the same thing. You could check it at time 0. You would have 1 minus p minus q to the first. And at time 1, you'd have the same beginning place. And you can check that, at time n plus n minus 1 here is the same thing you get if you do time n here. So it's not hard to check what I said is true. It's re-indexing it. And now you can actually combine this term with this sum. Because if you let j start at 0, then what's inside would be 1 minus p minus q to the 0, which is just 1. And 1 times q is q. And so that first term would be the q out here. So you can fiddle with the index a little more. 1 minus p minus q to the n plus 1 times the probability at time 0 being broken, plus the same sum, but just start the summation at 0 and let it go to n. And if you do that, when j is 0, you just get 1 in the inside, and 1 times q is this guy. So that's a way to combine these two terms into one. And this is what we wanted. This is saying that this equals this is exactly what the induction should show, because we want to show that the old formula holds when you just replace n by n plus 1. So n plus 1 appears here. And if you replace n by n plus 1, you would have an n up here, and everything else would be the same. Well, that's what you got. You got an n plus 1 here, and you got an n here. So we're done. Okay, so I decided to bite the bullet and do it just to show you how it works, because the formula is rather complicated by itself. And one could say, well, I'm not convinced that just because it works for 0 and 1 or 1 and 2, whatever it was, or 1 and 2, that it works in general. So this is how the induction proof works. Any questions? Good. Okay, now what? Well, now we can do some stuff with this and get some interesting answers. So, but even now, what we have is pretty cool. Let's go back to this formula. We're able to find the probability on any day you want that the machine is broken. And it's all in terms of what? The transition probabilities, the P's and the Q's, and the probability that it was broken on day 0. That's the initial distribution. So everything in this expression depends on something that's sort of hopefully known. You should know the probability that the machine works in big zero initially. Somebody that should know it, the manufacturer should know it. And the probability of these transition probabilities of going from a state of working to broken and back and forth, that also is assumed what we know. Now, there's something cool that happens here. Let me see if we can simplify this a little further now. Let's make a further assumption. So let's assume that P is strictly between 0 and 1. And the same is true for Q. So we're not allowing P to be 0 or 1. It's a probability, but it's not 0 and it's not 1. What does that do? Well, you see, if P were 0, then the diagram would look different. Once you're at 0, you can never leave because the probability of leaving would be 0. So that would really alter the way the diagram looks. And similarly, if Q was 0, you can never leave 1. And so forth. So these are sort of extreme positions that we don't want to have happen. So we're going to assume that we actually have a proper probability, P and Q, proper meaning what? Strictly between 0 and 1. Okay. And I'll give you a little hint. What we're interested in now, we're interested in what this expression looks like. So our interest is what happens as n gets large, or in the limit. Well, this is not the simplest looking expression in the world. So you could think, well, it's probably going to end up nasty, but actually it turns out to end up nice. So let's see what happens here. So under these assumptions, what happens if we add the equations? Well, 0 and 0 is 0, and P and Q add up to P plus Q. And if these are strictly greater than 0, this would still be strictly greater than 0. And this would be strictly less than 2. Okay, so we're assuming P and Q are both proper, that is, they're bigger than 0 and less than 1, then their sum is somewhere between 0 and 2. And our eye is on this expression here. So let's figure out what's going on with that expression. Well, there's a negative P and a negative Q in there. So let's multiply this inequality straight through by -1, just to flip everything. -1 times this will still be 0. When you multiply an inequality by a negative, you reverse the order of the inequality. Inside, these would become -P and -Q. This would get reversed. Again, you're multiplying straight through by negative numbers. That reverses inequality, and this now becomes -2. Okay. Now, with an eye on this, what happens if we add 1 to both sides, to everything here? So we add 1 throughout the inequalities. 1 and 0 is 1. When you add 1 to this, you have 1 minus P minus Q. If you add 1 to -2, you would just get -1. So this expression in the middle, 1 minus P minus Q, is strictly between 1 and -1. If you want, draw the picture. Here's the number line, here's 1, here's -1. And we're strictly in this interval. So it's like an open interval. We're somewhere in there. And why is that important? Well, that's important because that means 1 minus P minus Q is also a proper fraction. I guess it could be 0. But well, when I say proper, I mean it's not bigger than 1 and it's not less than -1. So it's like a probability, except it could be negative. But it's strictly between 1 and -1. That means this thing in here, when J gets big, should be getting small. Why? Because if you take a proper fraction and you raise it to a power, take like 2/3, and start taking higher powers of 2/3, it beats it down so that it approaches zero. So that's going to be a simplifying aspect to this. Now, there's something else we probably should notice here. This series is a geometric series. I think I mentioned it last time. What do you know about geometric series? I'm getting worried. I'm getting down by the end of my page here. So, okay, I'll push it a little further. Let's see. What's a geometric series? And a good example would be 1, 4, 8, and so on. It's a series you get by multiplying the first term by something, and then whatever you multiply that by, you keep doing that. Multiply this by the same thing. In this case, you're multiplying the first term by half. The second term by half gets you the third term. The third term by a half gets you the fourth term, and so forth. That's a geometric series. In general, they look like this. And typically they stop, say at this point, because if I go up to the nth power in my first power, then I'll actually have n terms. And the formula for this is equal to a times 1 minus r to the n, all over 1 minus r. Okay, and there's an even easier formula if it goes on forever. Because if it goes on forever, well, you have to add a condition. But if this is a proper fraction, which means a fraction between 1 and -1, then that will go to 0. And so then the whole formula just goes on forever. And on the right side, when you take a proper fraction to the nth power, it goes away. So what you just get is a over 1 minus r. Okay. I don't know how familiar you are with these formulas. I hope you've seen them before. Maybe you don't remember them. Maybe now that I've written them, you do. I know when I teach 3100, I usually go over this, but that doesn't mean everybody does. But even if you don't see it in there, it comes up, of course, in calculus. So this is stuff you should see somewhere. You may have to open the book and recall it. Okay, so what we're interested in is taking, let n go to infinity here. So actually, yeah, maybe keep this expression in mind up here. Yeah, why don't we see what's going on in the series? So with the series that occurs is this sum right here. So let's just rewrite it. This thing would start when j is 0. Well, there should be a j in here to begin with. Let's see if I'm doing this right. Well, that's the series that came up in the induction proof. But even if we go back to this one, then we would have n minus 1. I don't think it matters which one we look at because we're going to let n go to infinity anyway. So let's maybe let's look at the one that goes to n-1. So how would that look like? 1 minus p minus q to the 0th power is 1 plus 1 minus p minus q to the first power plus 1 minus p minus q to the second power, all the way up to 1 minus p minus q to the n minus first power. So we're just going up to n minus 1. That's what the thing looks like. And that pretty much matches this. There's a lead term. The lead term here is 1. The r would be what? 1 minus p minus q. That's what we're multiplying each term by to get to the next one. How many terms are there here? Well, there are n of them, because we're up here. And this sum formula kicks in. What does the formula say? A is 1, so write 1 that. In the parentheses, you have 1 minus r. But r here is the 1 minus p minus q. And that gets raised to the nth power. And on the bottom, you have 1 minus r. But that's 1 minus 1 minus p minus q. So I'm applying the finite form, the formula for finite, for the sum of a finite geometric series. This formula here, where I chose a to be 1, then I chose r to be what? 1 minus p minus q. Okay, so if you do a little more with this, there's not too much to do with the top. It is what it is. At the bottom, you can simplify. You can distribute the minus. In that case, the ones will go. And so what you get here looks like the top, which is 1 minus p minus q to the n, all over what, p plus q. That's what's on the bottom. Okay, so we now have an expression for the sum. Either in this one or in the one, why don't we go back to the original one? The probability on day n of being broken is this. So we have an expression for the sum here. So let's rewrite that one more time. So the probability that on day n you're still broken was equal to 1 minus p minus q. And what was it? Was it n or n minus 1? I'm confused, so I'll have to go back and look. I think it was n, because n was 1 less than this. So it's this times the probability on day, the first day initially that you're broken, plus we're really going up here. This sum here is what gets multiplied by q. So we have q times that sum. So it's q times, and that sum becomes this. 1 minus p minus q to the n, all over p plus q. So this is what we have by doing this sum using the geometric series. And let's rearrange the terms slightly, because something nice is about to happen. Let's distribute the q. So q times 1 over p plus q. So we'll keep this one the same, 1 minus p minus q to the n times p x naught equals 0. And then q times 1 over this is just what? Q over p plus q. And then when I distribute the q a little further, I have minus q times 1 minus q minus q to the n all over p plus q. So the probability that at time n we're broken is equal to this expression. That's a good place to come up for air. Does everyone see what I did? So I basically took what we already have proven, this equation here, and we recognize that this series is a geometric series, so we could actually get rid of the summation and get it in terms of something we know, which is what went on right here. It looks like this expression, and when you do that expression, you get this. So that carried over to this. And now I've just multiplied this through, picking up this term, this times this is just this. But now we're interested in what happens when n gets large. So let n go off to infinity. But remember, we've already argued that 1 minus p minus q is strictly between 1 and negative 1. So it's a proper fraction in that sense. It's not bigger than 1 or less than negative 1. So when you take powers of this thing is going to go to 0. Whenever you take a high power or proper fraction, be it negative or positive, doesn't matter, you're going to get close to 0, which means, and this is some constant, which means this whole term gets close to 0. Similarly here, the 1 minus p minus q to the n is getting close to 0. This stuff is some constant, but it doesn't matter. So the whole thing goes to 0. So what do you get in the limit? You get this. This is the only thing that doesn't depend upon n, and it's the limit. So the conclusion of this is sweet. It says the limit as n gets large of this is equal to p all over, not p, q, sorry, q all over p plus q. Well, you could interpret that as to saying, what's the chance? Oh, I forgot the p in here. What's the probability of being broken after a long period of time? It's this. Well, that's the probability of being broken. What's the probability that you're working after a long period of time? That would be the complement, right? So the probability after a long period of time that the system is working would be 1 minus this. But if you do the algebra, that's just change this to, common denominator is p plus q. And you get p over p plus q. So that's the companion result. So that's called a steady state probability. Something at the clock, I'm almost out of time. But it's not a bad place to end in that sense. After an infinite amount of time has passed, the probabilities that you're broken or working are these. These are called steady state probabilities. And they represent the probabilities of the system after a period of time. Okay. Well, let's bring it back down to earth. What was our initial example? Our initial example from Wednesday. Help me out. Remember it. I think there was a 75% chance of this, and I think there was only what, a 10% chance of this.
That's correct.
That's the probabilities we had, and then this loop would have to be what, 0.25, and this loop had to be 0.9. Now, that was our original numerical example from Wednesday. What was our initial distribution? Our initial distribution at the time, at the first day, initial, the chance that it was working was like 80%, and the chance it wasn't was 20. Okay, so I'm going back to my first numerical example, and I want to say, okay, what's the chance that the system is working, or let's say broken, because that's the first one we have here. What's the chance that it's broken after a long period of time? Well, that's this. So the chance that it's broken is Q over P plus Q. What was everything? This is P, and this is Q. So P plus Q is what, 0.85? And Q is just 0.1. So whatever this is, if you want to, I guess you could multiply top and bottom by 100. And that would get you 10. And that would get you 85 here. Right, and you divide by 5 now, this will get you 2. And you divide by 5 now, what would you get? 17. Yeah, that's right. So the chance that the system is down after a long period of time is like 2 over 17. That's the chance it's broken. What's the chance it's working? Well, that's this. Now I can go through all of substituting in, but it's pretty clear it's going to be what? 1 minus whatever this was. So that's 15 out of 17. That's the chance it's working. So if you drop into the office, now that's a 15, I guess. At this point. And you have to use a printer, and you haven't been in for a long time, like I haven't, because of the epidemic. One could guess, well, if this was actually correct, that would be a pretty good chance the thing is up and running, right? After a long period of time. Couple remarks. It doesn't really depend upon the initial distribution, right? Doesn't depend if this was a 20-80% chance, or these could have been reversed. There could have been an 80% chance it was broken at the beginning, and a 20% chance it was working on the initial day. The initial distribution doesn't really matter in the conclusion, because the conclusion just has P's and Q's, which are the transition probabilities, which is somewhat interesting. In other words, it doesn't really matter what the odds were on day 0, as long as you know what the probabilities of going back and forth on other days are. That's mildly interesting. It's independent of how things were when you first set up the machine. As long as you know these transition probabilities are the same, then you're going to get the same long-term probability. Questions? Okay,
And that's only in the case where the transitional probabilities are fixed from day to day.
that's correct. Yeah, we're only, yeah, and in fact, that's what we're, and for this class, we'll always be assuming that. We're not going to assume that those vary. So we're assuming that those things don't change from day to day.
Okay.
Now, what's the future? We're done with today, really. With the future, we're going to be doing this for more complicated systems. Now, by the way, this is supposed to be a Markov chain, but I haven't even talked about the Markov property yet. So everything we've done so far, you don't even have to have a Markov chain. So if you're telling me I don't know what it is, I'm telling you back, it doesn't matter. What was all of this based on? For this example so far, what did we really use? It's not on this page. Yeah, it is. We've used basic rules of probability. We use the probability tree, we use the multiplication rule, we use the sum rule, but those are just general schemes of probabilities. Now, are we done with the two-state guy? No, we're not done with the two-state guy. So here's coming attractions, and then I'll quit it there. Suppose we were in this numerical example right here. Suppose you wanted to know the probability that at time 0, the machine was working, and at time 1, it was broken, and at time 2, it was back to working. This is what I was going to do if I had more time today. So I'll just leave it as a tease. This is where we want to go next. Now, what is that? That's sort of like the joint probabilities we were doing. Remember when we did the review last week or this week, whatever? And somewhere along the way, I had you figure out the chance of getting two reds or two, a red and the white, or red and the yellow, and different things. These are called joint probabilities. And that's more complicated because you not only want to know whether you're going to, what we just figured out was this. If you want to know the probability at time 2 that you're at 1, we just did that. Because we figured out the probability at any point in time that you're either up or down, you're working or not. But this is a different kind of question. It's not just asking what's going on in day 2, it's asking what's the chance that initially it was working, then it broke, and then it got fixed again. The first 3 days were up, down, and up in terms of running. Okay, so in order to do this, well, let's make it easier. If you want to make it easier, just suppose you just wanted the first 2 days. What's the probability of these two happening? Well, you know what you got to do. You have to make a joint table. And now if I just cross off this last term, this looks pretty much like the review stuff, right? Day 0, you're either broken or you're working. Day 1, you're either broken or you're working. And so now the question is, how do you fill in the table? And the answer is, it's not immediately clear how you fill in the table. It depends. If you want to say the variables are independent of each other, well, then you know how to do it. But if you don't want them to be if you don't want them to be independent of each other, then that's where the Markov property comes in. And that's what we'll be talking about, I guess, on Monday. Where are we? Where are we in terms of homework? I think I assigned exercise 1, but I'm not sure we're there yet. I'm sorry to say. Let me look at it. I mean, you might be there on your own, but from my standpoint, no. I haven't covered what you need to know to do exercise 1. So I'm a little frustrated because I don't have even much homework to give you. I guess I could do this. Why don't I do this? Here's homework. suppose P is 2/5. Q is 2/3. Fine. Steady state probabilities. By the way, that's a one-line homework assignment. So in addition to that, I think I have to just fall back and have you do some reading. Try reading, maybe you've already done it. Page 4 is where we're at. We're starting slow. Don't worry about it. We'll get speed later. Read page 4, do this problem. I'll talk about it right after class if you like. Class is over. I'm going to take my usual 20 seconds to take my water break. Anyone who wants to see this simple problem done, or I think maybe you can do it without my help. But either way, just hang around for that. Anyone who needs advice about classes, because we're getting closer to the point where you have to sign up for things or not, hang around for that. Let's see if there's anything else I can tell you. I think that's pretty much it. Any questions before I sign off for the class? Cool.
Thank you, Professor.
Have a good weekend.
You too.
Thanks, Dr. Krennic. I'll see you next week.
Wait. When's Labor Day? I just thought about it.
It's not this Monday. I think it's next Monday.
Thank you. Good. Okay, because I'm talking like I'm going to see you Monday, and I figured that, but I got a little scared because we're getting close to the end of the month for sure. But I guess we're not quite there. All right, so I will see you Monday, if not sooner. All right. After that huge break of 20 seconds, I'm back. Did this stuff make sense?
Yeah.
Yeah, I thought it made sense.
I hope so. Got a little, I mean, if there's anyone here who wants to see the proof of the geometric series stuff, I'm happy to go over that.